Welcome. In this video tutorial I will illustrate how to integrate EyeLink eye trackers with experiments created using the stimulus presentation software PsychoPy. I will walk through the basic picture.py PsychoPy template that is bundled with the EyeLink Developers Kit and which illustrates the complete range of integration functionality. First though, we will cover some basic background information about how EyeLinks work and how the EyeLink Developers Kit is used to handle the PsychoPy integration. Tracking gaze with EyeLink eye trackers typically requires two computers. The host PC is provided by SR Research and runs our eye tracking software in a real-time operating system. The host software provides an interface to the eye tracker that allows the experimenter to set up the participant, perform calibration and validation, and monitor the gaze during data collection. The stimulus or display PC runs the stimulus presentation software, which in this case will be PsychoPy. Critically, the two computers communicate with each other via an Ethernet link. The display PC can send messages and commands to the host PC, and the host PC sends gaze data to the display PC, allowing gaze contingent tasks to be developed. The link also allows various camera setup operations to be performed using the stimulus PC screen. In order for this communication to work, it is important that you configure the display PC's Ethernet address appropriately. Please see the installation guide for your system or this FAQ on our support forum for further details. The EyeLink Developers Kit provides a set of core libraries written in the C programming language that allow other languages such as Python and stimulus presentation software such as PsychoPy, SiteToolbox and ePrime to interact with the host PC and control the EyeLink system. The Developers Kit will need to be installed on your display PC. In a typical eye tracking experiment, the Developers Kit libraries allow other software to establish a connection with the host PC via the Ethernet link, open an EyeLink data file on the host PC, specify various host PC parameters such as the calibration type, sampling speed, set up the participant camera, perform calibration and validation, start and stop recording data, send messages to mark critical trial events such as stimulus onset or participant responses, send data viewer integration messages to facilitate subsequent analysis, and transfer the EDF file to the stimulus or display PC at the end of the task. For more information about the EyeLink Developers Kit, please see the EyeLink Programmer's Guide, which can be found at these locations. EyeLink integration with PsychoPy is handled via PyLink, a Python wrapper for the core libraries provided in the EyeLink Developers Kit. PyLink is used to handle the EyeLink integration for experiments that are programmed in Python itself and experiments that are created with Python-based software tools such as PsychoPy, OpenSesame, and even our own experiment builder software. PyLink implements all of the functions and classes required for EyeLink connection and graphics, such as the transfer and display of the camera image to the display PC, calibration, validation, and drift checks. Each of these operations can be called with just a few lines of code. For detailed information about PyLink, please see the PyLink user guide provided with the Developers Kit, as well as the Getting Started with Python and PyLink PDF guide, which also contains a detailed walkthrough of the picture.py template. For PsychoPy integration, we have created a special Python library called EyeLink Core Graphics PsychoPy. This library implements a set of methods that will be used to handle the graphics for core eye tracker functionality, such as image transfer, calibration, validation, and drift checks. So for example, when the calibration routine is evoked, PyLink will use the methods defined in this library to draw the calibration and validation targets, play the warning beeps, etc. The EyeLink Core Graphics PsychoPy library can be found in all of our PsychoPy example projects and should be placed in the same folder as your experiment code, along with its dependency files, which include audio and calibration target image files. Getting started with EyeLink and PsychoPy integration is very straightforward. There is a very comprehensive post in the Learning Resources section of our support forum that outlines all the steps you'll need to take, along with some useful links. In brief, you will first need to make sure that you have configured the Ethernet settings on your stimulus PC to allow communication between it and the host PC. Typically this involves setting its address to 100.1.1.2 with a subnet mask of 255.255.255.0. Detailed instructions for all operating systems can be found in the user manual and in this thread on our support forum. Next, download and install the EyeLink Developers Kit from our support forum. The link is below and in the video description. Then make sure you've also installed the latest version of PsychoPy. Finally, make sure that you copy the appropriate PyLink folder from the Developers Kit into your PsychoPy installation. PsychoPy already comes with a version of PyLink, but this last step ensures that you're using the most up-to-date version. For example, the version of PsychoPy that I'm using in this video is based on Python 3.6, and I'm running 64-bit Windows, so I copied that version of PyLink into the Site Packages subfolder of PsychoPy. The exact location of these folders may vary depending on your operating system and installation, but complete instructions can be found in the Getting Started with PsychoPy guide on our support forum. So let's take a look at the picture.py example script. After installing the EyeLink Developers Kit, it can be found in the PsychoPy examples subfolder of the Python sample experiments. You may not have write permissions in this directory, so to run the project, please copy it to somewhere like your Documents folder or desktop first. The picture.py task is a very simple task that presents two images twice in a random order, and for each image records gaze for 5 seconds or until a key is pressed. Most of the code in the script is designed to illustrate the full range of EyeLink integration functionality that is possible via PsychoPy. You may not require all of the components in your own script, but it can be useful to know what is possible. Please note that the picture.py template was created using PsychoPy's Coder interface. The Builder interface provides some basic eye tracking functionality, but it is currently quite limited, and we strongly recommend that you use the Coder interface and the approach outlined in our example scripts when creating eye tracking tasks in PsychoPy. The script illustrates the following functions. It establishes a connection with the eye tracker, sets various eye tracking parameters such as screen resolution and the calibration model, opens an EDF file on the host PC to store the gaze data, allows the experimenter to perform camera setup and calibration validation. It starts and stops the eye tracker recording for each trial, sends messages to the EDF file that mark critical trial events such as stimulus onset and participant responses, sends data viewer integration messages to facilitate subsequent analysis, and finally closes the EDF file at the end of the recording and transfers it to the display PC. Before we go through the code itself, let's quickly run the task and take a look at what the participant sees on the stimulus PC screen. Then we'll see what the experimenter sees on the host PC screen, and finally we'll take a quick look at the data in Data Viewer to see how the Data Viewer integration works. After launching the task, the first thing that happens is that it asks for the file name for the EyeLink data file. I'll leave the default test file name. Next we see some basic task instructions, which include the advice to press enter twice to calibrate the eye tracker. Pressing enter allows the camera image to be transferred, and we can use the left and right arrow keys on either keyboard to switch between the thumbnail and global camera views. Having checked that the participant is set up optimally, the calibration process can be launched by pressing the C key on either the display or host PC keyboards. Everything looks good, so I'll press C to start the calibration. As you can see, the calibration targets appear one after the other. Typically this would be followed by a validation, but I've skipped that to keep things short. If the calibration and validation are good, the Enter key is pressed to save the calibration, and then the O key is pressed to switch the host PC into output or record mode. This starts the experiment, with each trial beginning with a central drift check target, followed by an image which remains on screen for 5 seconds or until a key press. This sequence is repeated a total of 4 times. At the end of the task, a message is briefly displayed indicating that the EDF file is being transferred from the host PC. Now let's take a look at what the experimenter sees on the host PC screen when the task runs. During the calibration, the targets appear one by one, along with a representation of the raw pupil-CR data in uncalibrated space. Again, I've skipped the validation to save time. After the calibration, the drift check target appears, and when the experimenter presses the spacebar or Enter key on the host PC, the recording starts. As you can see, the trial image also appears as the backdrop on the host PC recording screen, along with a blue central rectangle. As we will see when we look at the code, the rectangle indicates the location of an interest area that is not visible to the participant. The host PC also displays a status message that allows the experimenter to keep track of which trial is being run. When the experiment is finished, we can open the EDF file with Data Viewer. Note that the EDF file has been renamed on the local display PC. In Data Viewer, we can see that the recording has been parsed into 4 separate trials. We can click through the trials and see that the relevant image is being shown as the backdrop in the spatial overlay view, and each trial contains a single central interest area. If we toggle on message visibility, we can also see the various messages that are flagging key trial events such as the onset of the image and the blank screen that ends the trial. These messages can be used to set an interest period in Data Viewer. Finally, if we open the trial variable value editor, we can see 3 variables: condition, image and RT. The RT variable shows a default -1 value for each trial because I did not press a key to terminate the trial. So let's take a look at the template itself and see how it works. Like most Python scripts, we start by importing the various modules that are required, including PyLink and the critical EyeLink core graphics PsychoPy module, which will handle the camera setup and calibration graphics. The following lines of code set the working directory and make sure that the PsychoPy console only logs critical messages. The Use Retina flag can be set to true if the task will be delivered on a Mac with a Retina screen. The dummy mode parameter can be set to true if you need to test the script without being connected to an eye tracker. I'll talk about this in a bit more detail shortly. The final flag ensures that the task runs in PsychoPy's full screen mode. These lines of code just set up a variable that contains the trial images and condition variable labels for the task. At the beginning of the script, we first prompt the experimenter to specify an EDF data file name that will be used to store the gaze data on the host PC. For compatibility with older versions of our hardware, the file name opened on the host PC should not exceed 8 characters and should only contain letters, numbers and underscores. This code simply checks that the file name is valid. Next, a folder is created on the stimulus PC to store a local copy of the EDF file when it is transferred at the end of the experiment. The local copy of the file is renamed by appending the current date and time to the file name. At the beginning of an eye tracking experiment, we need to establish an active connection to the host PC. The connection is required so that the experimental script can send over commands to control the eye tracker and receive gaze data if desired. The command for initializing a connection is pylink.EyeLink. This function takes just one parameter, the IP address of the host PC. If you omit the IP address, this method will use the default address of the EyeLink host PC, which is 100.1.1.1. The function returns an object called el_tracker in this script, which contains methods that will be used to handle key aspects of the integration, such as the sending of commands and messages to the host PC. The eye tracker in your lab may not always be available, or you may find it more convenient to debug and test your experimental script on a computer that is not physically connected to the EyeLink host PC. If your script does not rely on real-time eye movement data, you can set the dummy mode variable that we saw earlier in the script to true. The if statement at the start of this code section checks whether the dummy mode variable is true, and if it is, it opens a simulated connection to the tracker. This means that the script can be run without having to comment out all of the EyeLink integration code. If the dummy mode variable is false, the pylink.EyeLink function is called and the connection is assigned to el_tracker. These lines of code close the task down if the connection to the eye tracker fails. Next, we concatenate the EDF fname variable with .edf and assign that string to a variable named EDF file. Then we actually open an EDF file on the host PC by passing this EDF file variable to the open data file command. If this operation fails for some reason, we print an error and close the connection to the host PC. These 2 lines of code allow you to write some preamble text to the header of the EDF file, which can be useful at the analysis stage. Many eye tracking parameters can be changed directly via the host PC interface, but in some cases it can be useful to change these parameters via your experimental script. In these lines of code, we first put the eye tracker into offline mode so that it is ready to receive and act on commands, and then check what version of the host software is running. The following lines of code essentially ensure that all available event and sample data is both being stored to the EDF file and sent over the Ethernet link to the stimulus PC. Starting with the event data, the code assigns a text string containing all the event data types to two variables, one for the file data and one for the link data. Different EyeLink eye trackers have different functionality with respect to what data is available at the sample level. So the if clause is just a check to make sure we are not trying to tell the host PC software to save or stream sample data that isn't available. Again, all available options are assigned to a text string. These final four lines pass the text string variables as a parameter to the appropriate command, which is sent to the host PC via the eltracker.send command function. The same eltracker.send command function is also used to set the calibration type to a 9-point model and to allow a button box to be used during the calibration process. In the next step, we create a graphics window, which will be used to present the calibration targets and the experimental stimuli. The monitor's native pixel resolution is passed to the SCN width and SCN height variables. The if clause handles drawing issues that can occur with retina displays by rescaling these values appropriately. We then construct a string containing the pixel coordinates for the top left and bottom right pixels and pass this to the host PC using the el_tracker.send command function. We also construct a similar string containing the text display_coords along with the pixel coordinates and use the eltracker.send message function to write this message into the EDF file. Data Viewer will use this message to ensure that things display correctly at the analysis stage. The next step is critical. It involves the EyeLink Core Graphics PsychoPy library that we imported at the start of the script. As mentioned earlier, this library implements a set of methods that will be used during camera setup, calibration, validation and drift correction. So EyeLink will use the methods defined in this library to draw the camera image on the stimulus PC display screen, as well as draw the calibration and validation targets. First, we create a graphics environment instance called GENV in this script by passing ELTracker, the tracker connection, and Win, the graphics window we plan to use, as parameters to the EyeLink Core Graphics PsychoPy library. Having created a graphics environment instance, we can now adjust some of its critical parameters. For example, we can set the foreground and background colors of the screen during calibration and choose what kind of calibration target we would like to display. The default target is a simple circular target, but the picture.py template illustrates how to use an image file instead. We simply set the target type to picture and provide a path to the image that we want to use. Next, we turn off the default calibration beeps. This if clause applies the fix for retina displays if it is required. Finally, we call the PyLink.openGraphicsX function to let PyLink know that we want to use this window and these parameters for the calibration. The next section of code defines some helper functions that do things like clear the screen, draw messages to the screen, terminate the task gracefully, and actually run the trials themselves. I'm going to skip over these right now and come back to them a bit later. As far as the EyeLink integration is concerned, the next critical step involves putting the host PC into camera setup mode so that the experimenter can set up the participant and do the calibration and validation. This code displays a message, the last line of which depends on whether dummy mode has been set to true or not. The next lines of code check that dummy mode is not set and then calls the eltracker.doTrackerSetup function. Now that we have set up the graphics environment and configured our calibration preferences, this single line of code is all that is required. The except throws an error if the attempt to put the host PC into camera setup mode fails for any reason. The final lines of code simply prepare a trial list, shuffle it, set up a trial index variable, and then a for loop calls the runTrial function, passing the trial information and trial index as parameters. Finally, the index variable is incremented, and when the for loop exits, the terminate task helper function is called. So let's go back and take a look at those helper functions. This first helper function just clears the screen. The second displays a message and optionally waits for a key press. The terminate_task function is an important one. It gets called at the very end of the script after the main trial loop is completed. The code first updates the EL_tracker object with the pylink.getEyeLink function, then checks whether the connection to the EyeLink is still live, and if it is active, whether a recording is still in progress. If recording is ongoing, then the abort_trial function is called. We will take a quick look at that function shortly. Once we are happy that we still have an active connection and are no longer recording, we put the eye tracker into offline mode, which is the state it likes to be in when receiving commands. We clear the recording screen on the host PC, wait a short duration, and then close the EDF file. Next, we show a message that indicates that the file transfer is in progress, and create a local_EDF variable that stores the path and file name for the copy of the EDF file that will be stored locally on the display PC. Finally, we try to call the received data file function, passing the EDF file name on the host PC as the first parameter and the local path and file name as the second parameter. Finally, we close the connection to the eye tracker, close the window we are using for the task, and quit PsychoPy. This is the abort_trial function that gets called if the terminate task function is called when the tracker is still recording. It simply updates the EL_tracker object and then checks whether recording is indeed ongoing. If it is, it stops the recording. The abort trial function then clears the recording screen on the host PC and writes a couple of messages to the EDF file. The return value can be used for error handling. Let's move on to the main run trial function. It takes the trial parameters and trial index variables as its input. First, it unpacks the trial parameters for the current trial from the trial paths list into the cons and pick variables. Next, PsychoPy's visual.imageStim function is used to load the image to the display window. Next, the EL_tracker object is updated and the tracker is put into offline mode so that it is ready to receive commands. The first command simply clears the recording screen on the host PC. The next section of code is very useful. It passes a copy of the image that will be displayed to the participant to the host PC so that it can be used as a backdrop during recording, allowing the experimenter to monitor gaze accuracy and participant compliance during the trial. To do this, we first open the image using Python image library's image.open function. Then the image is resized to fill the screen as it is when it is actually shown to the participant. The next lines of code pass the RGB values for each of the image pixels into the pixels variable, and then call the bitmap backdrop function and pass the screen parameters and the pixel RGB values to the host PC. The host PC can also draw primitive shapes such as lines, rectangles and crosses, as well as text. In this next section we use the drawFilledBox function to draw a small rectangle in the center of the screen. As we saw earlier, this rectangle represents the location of an interest area. The full range of supported drawing functions are listed in the commands.ini file on the host PC. The code simply determines the left, top, right and bottom coordinates of the rectangle and builds a string which passes those values as the first four parameters of the drawFilledBox command. The final parameter, 1, is the color, in this case blue. The last line of code uses the .send command function to pass the drawFilledBox command and its parameters to the host PC. This next line of code uses the .sendMessage function to write a message into the EDF file. This message will be used to define the start of the trial in DataViewer. Here we build a string called statusMessage and pass that string as the parameter to the record status message command. This is what allows us to see which trial we're on in the message area of the recording screen on the host PC. Before each trial starts, we initiate a drift check. This is a critical part of any eye tracking experiment, as it allows the researcher to ensure that the eye tracker is accurate before any data is actually collected. A few seconds checking that the tracker is accurate before each trial starts can save a lot of time and frustration at the analysis stage. The code checks that we are not in dummy mode, and if not, checks that the tracker is still connected and that the break key hasn't been pressed. If either of those are the case, then the terminate task function is called. If neither are the case, the code tries the .doDriftCorrect function and passes the XY coordinates for the drift check target in screen pixels. The last two parameters are defaults and ensure that the target is drawn and that the escape key can be pressed in order to return to the camera setup if necessary. Finally, the tracker is again put into offline mode with a setOfflineMode function so that it is ready to receive further commands. The next section of the code calls the .start recording function and passes the default parameters which ensure samples and events are both stored to the EDF file and made available over the link. A short delay is added to allow the eye tracker to buffer some samples. This buffer is important as internal velocity calculations are based on a window of samples. After the delay, the graphics window is cleared, the trial image is written to the back buffer, and then the win.flip function is called to make sure that the image appears at the next monitor retrace. As soon as this call clears, we use the .sendMessage function to flag the image onset time in the EDF file. We also store the image onset time to a variable. As we will see later on in the code, we need to know when the image was shown so that we can terminate the trial 5 seconds afterwards. This section of the code illustrates some useful data viewer integration. This is the code that allows the images to appear in the spatial overlay and animation playback views in Data Viewer. Anytime you see a message being written to the EDF file that starts with !V, then this will be a message specific to Data Viewer. First, we clear the screen in Data Viewer to a neutral grey background colour using the !V clear command. Then we assign the path to the current trial image file to the bg_image variable, then build a string containing the !V image load center integration command and pass the image path, screen center in pixel coordinates, and the image width and height. This allows Data Viewer to find the relevant image and present it in the correct location and with the same dimensions as it appeared to the participant during the recording. We also define a single interest area that matches the size and location of the box we drew on the host PC screen. This is done by assembling a string containing the !V eye area rectangle integration command, a numerical index, in this case 1, and the left, top, right and bottom screen pixel coordinates of the interest area, in this case simply borrowing these values from the variables we created to draw the rectangle on the host PC screen. This section of code ensures that the image is shown for 5 seconds or until a key is pressed. We start a while loop that will keep running as long as the getKeyPress flag stays false. If the getKeyPress flag remains false, a timeout message is written to the EDF after 5 seconds. Then the code checks that the tracker is still recording and runs the abort trial function if it is not. This code checks to see whether a key has been pressed. If the spacebar was pressed, we send a key pressed message to the EDF file and update the value of the RT variable, and change the getKeyPress value to true, terminating the while loop. If the escape key was pressed, we send a different message, trial skipped by user, to the EDF, clear the screen and run the abort trial helper function. Finally, if Control and C were pressed, we send a terminated by user message and run the terminate task function. So the while loop exits after a key press or 5 seconds have elapsed, and we clear the screen and immediately write a message to the EDF file. This message can be used to define the end of an interest period that spans the time that the image was displayed. The code sends a Data Viewer integration message to indicate that the screen should be cleared at this point in the animation playback. We wait 100 milliseconds to provide a buffer and then call the .stop recording function. These 3 lines of code also start with !V, so are also Data Viewer integration messages. Each one provides a variable and its value, which can be used to group and filter the data at the analysis stage. The variables that will appear in Data Viewer are condition, image and RT, and their values are provided by their respective variables in the script. Finally, the end of the trial is signalled with a trial result message. By default, Data Viewer will use this trial result message to segment the data into trials, but it could also be used by any other analysis software. And that takes us to the end of the main run trials function. We have already been through the remaining code. So, to summarise quickly, a comprehensive EyeLink integration in PsychoPy involves using both PyLink and the PyLink Core Graphics PsychoPy libraries to perform the following tasks. First, the PyLink.EyeLink function is called to establish a connection with the eye tracker. This function returns a tracker object that contains methods that will be used to handle the communication between the PsychoPy script and the EyeLink system. Next, an EyeLink data file is opened on the host PC via the tracker object.openDataFile function. Various host PC parameters can be set, typically via the tracker object.send command function. The EyeLink Core Graphics PsychoPy library is used to create a graphics environment that can be used for tracker-related tasks such as camera setup and calibration, as well as for stimulus presentation. Camera setup and calibration validation are performed by calling pylink.openGraphicsEx and passing the graphics environment as a parameter. During the task itself, the host PC can be instructed to start and stop recording for each trial, and accompanying messages sent to the EDF to facilitate subsequent data analysis. Further messages can be written to the EDF that mark the onset of critical trial events. When the task finishes, the EDF file on the host PC is first closed and then transferred to the display PC using the .receive data file function. You can also send a wide range of data viewer integration messages, such as background images, variable labels and values, interest areas, etc. For a full list of data viewer integration messages, please see section 7 of the Data Viewer User Manual. I hope this video walkthrough was useful. Please do check out our other PsychoPy templates, which illustrate further integration features, including how to read gaze events and samples over the link. Finally, if you have any questions, please don't hesitate to get in touch with us, either via the support forum or by email.